unidentified anomalous phenomenon.
The scientific endeavor sponsored out of a very prestigious university.
What's left in our data set that the model just cannot figure out? There's something anomalous going on, and clearly no one in the public has figured it out.
I'm hoping for a big discovery in my lifetime.
It may affect how we understand reality, and it could open up areas of science and technology that could be used for the greater good.
I am pleased to welcome Ezra Kelderman to this conversation. Ezra is a project manager for Project Galileo. So maybe we could start off by having you introduce yourself and maybe give us a quick background on Project Galileo for the people who don't have the background. Also mention the sponsoring institutions and things like that.
Sure. Yeah. Thanks for having me, Tony. So yeah, I'm Ezra Kelderman. I'm a project manager at the Galileo Project. Started, with the project probably about a month after its inception back in, I believe it was July, August 2021. And that really formed off the heels of the 2021 report from the Pentagon on UAP. It was sort of a landmark date, and Professor Avi Loeb, formed the Galileo Project out of the University of Harvard, or Harvard University. So yeah, a lot of Avi's work prior to Galileo. He's with the Black Hole Initiative, and probably where most people have heard of him is in his studying of Oumuamua, the interstellar object that came through our solar system and behaved kind of strange, just not as expected as most objects would. So yeah, he did a lot of studying into that, and theorized on, this may not be a natural object. So of course, Oumuamua left our solar system rather quickly. We didn't get a whole lot of information on it. And so that is part of what the Galileo Project is interested in, both interstellar objects and what's happening within our atmosphere. So that's kind of the UAP side of things. Both are very different activities, but yeah.
And we should define what UAP is for the people that are new to this topic.
Sure. It's the acronym keeps changing, but it's unidentified anomalous phenomenon. So as most people know of UFOs, the flying part of it isn't necessarily accurate. Some of these anomalous objects may not be flying in the conventional sense of like an aircraft. And you also have a lot of reports of submersible objects or transmedium objects that come out of the ocean or go into the ocean, space, atmosphere, underwater. So it kind of broadens it and focuses on more the anomalous nature of these objects.
And the Galileo Project, so is this project housed entirely, well, actually, I shouldn't say housed, but maybe sponsored by in the most part by Harvard, where I know you're drawing from scientists and staff from all over the world, but is this when I say Galileo, it is a Harvard University project, correct?
It is, yeah. So we are we're a Harvard research project, and like you said, we have members from all across the world, different universities. But yeah, we're sort of a unique project, something Harvard hasn't seen a lot of, especially the scale of our activities and how how our operations work and how far-reaching they are. But yeah, technically we're Harvard sponsored or Harvard research.
And which department is it out of in Harvard?
Yeah, it's out of the Astronomy or Astrophysics, Center for Astrophysics.
Right. So the reason I wanted to kind of draw attention to this, because, as soon as we mention the word UFO, people start thinking all sorts of things. And I think it's important to emphasize that everything we're talking about is a scientific endeavor. And there's huge amounts of speculation around this topic, but what I'm talking to Ezra today about is the scientific endeavor sponsored out of a very, very prestigious university and from a science department. I did a bit of reading on the Galileo project on the website. It sounds like there's like three main categories. You correct me if I'm wrong. There's interstellar objects, which could be far away, like it could be on the edges of our solar system and beyond. There are, I guess, meteors that could end up on Earth that come from interstellar space. I don't know if that's its own unique category. And then there's UAP, which are more near Earth phenomenon. Is that, or is it just two categories? Help me understand like what the buckets are of the research you guys are doing.
Yeah, I think the way you broke it down into three is pretty accurate in terms of the sort of milestones and how we investigate things. There's two main categories, the interstellar objects, the UAP, but there's very different funding levels required between meteorite investigation. Something crashing on Earth is astronomically cheaper than building some sort of sensor array that goes up on a satellite, or even something that rendezvous with an interstellar object going through the solar system. And we'd love to eventually get there, but that's like such a huge magnitude difference in funding. That's where we get into billions of dollars to be able to do, but we'd love to get there.
Yeah. So the thrust of the Galileo project is looking for things that potentially are not natural. These kind of, whether it's an object crashing through our atmosphere and landing into the ocean, or an object deep in space, or things nearer to Earth. The idea is like, hey, let's look for things that possibly are not of natural origin. Let's figure out what these things are. That's could I say that's the thrust of Project Galileo, is just, and you're looking in various places for these objects.
Yeah, I think that's sort of the shiny goal of the project. Whereas, to get to that, we have to understand what's even an appropriate scientific process for delving into that, for getting a high resolution image, or finding some detection method for something we don't have a process established for. So I think really the foundation of everything and what we're doing is really spearheading or pioneering an appropriate, rigorous scientific process for studying this sort of wide array of anomalous objects. We may, who knows if we'll ever get that high resolution image or detect something we can classify, but we've already come a long ways in laying the groundwork for how to even approach this problem. And we've had to learn it along the way, obviously, in developing it. But, some of the most valuable things that could come out of this and are coming out of this are really understanding how to apply as many modalities as possible and have them communicate with each other. We're talking infrared, radio frequency, all of these different ways to observe our reality or what's around us. How do you build a system and make it work together and be as comprehensive as possible? So that's a lot of what we've achieved so far, and then it's slowly getting into, okay, now what do we see with it, and then we'll build on that.
Like, to what extent is this data going to be shared, available to other researchers? Like, I think there's true benefit in doing this in more in an academic context, because there's going to be more sharing of information. But is that the intent of Project Galileo? Is to provide data that other researchers can take a look at.
Yeah, absolutely it is. Now, when is it appropriate to kind of open source everything? That's a little bit of a trickier question because obviously we want to be able to do our analysis on that, get published papers out on what we found in our data, because there's obviously a lot of context behind what's in our data that, we want to be careful about not misrepresenting or leading the public in the wrong direction through their analysis as to what's in this data. But overall, our entire goal is to be completely open with the public. We really want to get into citizen science, both in, people having their own hardware stations and those mesh connect to other people's observatories. So that's, in the long run, that's where we're trying to get. So, we are coming out with some published papers, one's in peer review now. And I hope that, once that is out and for the world to digest, that, we can also like provide the data with that. Now it's like terabytes and terabytes of data, but yeah, that's where we hope to get, where we can share everything as we go, along with how we do this. How is the system built, and how does it connect with? How does each instrument connect with like their edge computers, and how did we get here? And so, yeah, that's information we're sharing in our publications as well as we go. And we'd love to see other people build similar observatories to ours and collaborate. I mean, the end goal is to try and solve this problem of both how does one study this and what's out there. That's the end goal.
I guess maybe if I were to refine my question, it's not so much making the data available, because you're going to put some intelligence on it and analyze it. But I think what's great about having this in an academic setting is that there's a drive to publish. The intent is not to keep it, whereas you're never sure in a government agency how much they're willing to share. So in a way, I feel like we will probably be seeing more coming out of these more academic-led efforts. The paper that you're saying is in peer review, is there a preprint available for that, or is that not even available as a preprint?
There is, and I'll share that link with you too. Yeah.
Okay, great. I'll share that in the show notes. Okay, so let's get into more the methodology and the instruments you're using, and maybe start with essentially you're looking at the sky, right? Like these are just different ways to look at the sky to figure out, is there something interesting out there? Take us through some of the thinking, the instruments you're using, the methodology.
Sure. Yeah. So I think some of the initial steps in our early brainstorming came down to kind of the obvious in your face way to monitor the sky, and that's with optics, right? Everyone thinks telescope, cameras, the works. And so then you have to think about, okay, we're not setting up like an ordinary telescope to observe the stars, and we want to be able to see from the horizon all the way around, and obviously want to cover the visible light spectrum. And then it took a lot of the team going through thousands of reports on this topic, which is a tricky area, right? Because if you want to approach something with scientific rigor, the data has to be supported. But this is a topic we don't have that precedent established. We don't have this clear cut. This is what you're looking for. These are the properties or the attributes of your target. So, we're really thinking we got to throw everything at this to figure out what works. So yeah, scoured a bunch of reports, and infrared comes up as an obvious modality to examine as well. So optics were really the starting target of how to develop an observatory of instrumentation. And then, obviously radar, what's the other data out there that's already being taken, and how do we integrate with that or kind of create our own version of that? One example of that might be like ADS-B, or how airplanes transpond. That's public information. You can track that.
What is that? What is that? ADS-B? What's it stand for? What is it?
Oh boy, I don't know that. Yeah,
there's a lot of acronyms, but tell me what it is.
Yeah, there are tons. But to follow FAA rules, every like civilian commercial plane has to have a transponder, and that's sort of the radio frequency identifier that shows their location. Like air traffic control, they're relying on ADS-B signatures transponded from all aircraft. Now the military doesn't. I think in some cases where it might be like, let's say it's considered a national security threat to transpond, they don't necessarily have to transpond over that network. So there are occasions where if you pull up, whether it's Flight Radar 24, or there's several sites that you can just monitor the map of transponding planes. There's occasions where there will be an aircraft that just isn't transponding. But, if you consider something like 99% of all aircraft transponding, then that's a really interesting data point for us to be able to filter and just kind of add that layer of data onto the objects that we detect, so we can, quickly filter out anomalies if there are any.
Yeah. Isn't the problem, you don't know exactly what you're looking for other than things that are unusual. And that's why the problem scope is actually, it's quite large, because it's a little bit undefined exactly what you're looking for.
It is, and you have to navigate that balance of, there seems to be something to a trend in reports from people across the globe for decades. There's got to be information from that we can glean to at least focus on or dial some of our instrumentation into what we're planning to observe or what we expect to observe. But the responsible thing to do is to keep it as wide open as possible. So yeah, it's a tricky balance, but at the end of the day, we're throwing everything at this to see what pops up, in these modalities.
In the modalities you mentioned, which are the ones where you're building instrumentation? Which are the ones where you're just trying to integrate with existing data? I'm assuming this ADS-B is just, it's information that's already available that you're trying to bring into the mix. You mentioned optics, infrared radar. Does your instrumentation cover all these aspects?
It does. And, month by month, we're continually working towards, so like an example where we're at right now is we can have our all sky infrared camera running. Let's say an aircraft flies by. The software will detect that movement of that object, and it'll draw a bounding box around it. So once it's kind of through post-process, you will have a video of, objects flying around, little bounding boxes drawn around them. It'll give it an identifier, and it'll also log the trajectory of each object. So once everything's kind of analyzed and narrowed down, you can get plots of trajectories labeled by what object they are. So that's sort of the sort of pathway through everything is, first detection. We need to be able to just show that we're detecting things. Then you want to start getting into tracking, where you might have higher resolution, 40x optical zoom type cameras that can lock onto these objects and get you a much better view of them. And then ultimately you get to a point where, okay, with this information collected, I can now start to classify or assign characteristics to these objects. A lot of those can be already bucketed or categorized by, like we talked about, the ADS-B signatures. And, we're in a position now where we could start tagging these objects in the video with the ADS-B information. So it'll say, 737, 747, whatever airplane identifier it has, it can be overlaid onto the data. So we're always working in that direction of almost having like a dashboard of narrowed down detection windows in terms of time, where you can just look through. We had 30 detections today, and you can look at all those. And having the raw data in an appropriate arrangement for the AI tools to digest them properly and have an effective analysis.
So you mentioned this process of detection, tracking, classification. So are you primarily using infrared for the detection, and then if there's something worth looking at closer, that's when the optics come in? Is that typically how I guess the process?
Yeah, and that's a little bit, I would say that's a little bit forced by the technology itself. It's probably the highest quality infrared camera we can get might be, and I don't even know if we can still get our hands on this, but like a 1024 by 512 resolution. What we're using in our system, our Dalek system right now, which is the all-sky infrared, it's 8 cameras that are 640 by 512. Now, one of those cameras costs $6,000, $6,500 a piece. And for a visible camera of that quality, you're looking at, what, $20? So it's a bit forced by what tech is available, where obviously the lower resolution modality is going to be better suited for telling the rest of the system, hey, heads up, we have some movement over here. Throw something higher quality in that direction. And that's where we also have a visible all-sky system. So that's going to be lower resolution, high field of view to aid in that detection, because it will be, it could be an important data point if something is detected in infrared but isn't visible, which is something that is commonly reported. We just don't understand, the truth behind that or what's going on there. And you may also have something in the visible that isn't being seen in the infrared.
Yeah.
And so having both of those
That's
modalities,
also weird.
it is very weird. Yeah.
Yes.
And there are, claims of that going on with this drone situation in New Jersey. I think there's maybe one or two instances, but
for the uninitiated, what that would mean is like there's this object being propelled in the sky, but there's no heat. So what gives? That's also a mystery. Like this. When you say all sky, like when you put up this system, you're not seeing it's not the all of the sky, right? It's all of the sky from that particular point. And how much of all sky is all sky? It just, to me, it just seems like it's this needle in the haystack where you're just looking at a teeny tiny percentage of the sky. Can you say how much percentage of the sky one of your system covers? Is it 1%? Is it 0.1%? Help me understand the scale. I truly don't know, like how much of the sky you're actually seeing.
Yeah, and that's an important question, because it does, our quote unquote all sky systems will see nearly all of the sky from that point of view, right? But is it effective only to 1 mile out 10 miles, 100 miles, because then you have a real problem where, and this is what we refer to as detection volume. You know, we want to have as far of a detection volume as possible, or else it leads you to the issue of, well, shoot, we got to set up a site every mile. We have to spread these out in a giant mesh network. Because yeah, like that's where triangulation comes in as a really important factor.
Oh, I see.
First, we have to determine what is the detection volume for each modality. And so for instance, for our infrared all sky, we're still kind of testing the bounds on that. And obviously what matters most is what's the size of the object you're detecting. So we could probably see a large commercial plane out to, I don't know, maybe 20, 25 kilometers. But if we're dealing with something the size of a car or smaller, then obviously that detection radius comes down quite a bit. So then we have to really consider, okay, we need to set up multiple stations, both to increase that detection volume, but more importantly, to give us a reference point for understanding the actual distance to the object and the size of the object, and even the kinematics, like how fast is it moving? Is it accelerating? And really with one observation point, you technically can't understand the size of anything or its speed, any of the kinematics you won't be able to determine because you don't know if it's right in front of your face or, miles away. And that's especially important for this problem where you don't have a precedent. You don't have attributes that are already known for what you're looking for. If you and I stand outside and we see an airplane fly over, our head knows, we know in our mind what an airplane size is in general. And so we can quickly just be like, oh, that's, a couple miles away, because we have that cataloged in our head. But with this problem, we don't have this taxonomy of, oh, that's a triangle craft. We know those are, 200 feet across. So it makes it a really challenging problem, and it makes triangulation so much more important.
Triangulation meaning like you have to have multiple sensors, like you need to look at the same object from multiple vantage points, which means that this means that typically your observatories are not deployed in standalone fashion. You're deploying a group of them. Is that true?
Right, and that's the point we're at right now. That's our main focus, the last few months into probably the coming months, is to build on that primary or main observatory we have set up, and then set up these stations several kilometers away with duplicates of, for instance, that infrared all sky. We need to set up 2 or 3 more at these ranges that optimize our detection volume. We want to go as far as possible to get that sort of wider angle at a faraway target. But if you go too far, then you exceed kind of the range of what the camera is capable of detecting.
So the numbers you threw out earlier, like this idea of like for a larger object, maybe you can see up to 25 kilometers, but as the object gets smaller, then of course that distance shrinks. So you can imagine these systems you're putting in place have like this, like the sphere of like 25 kilometers that they're observing. But for smaller objects, it kind of comes back for a drone size object. Is that like a half a kilometer, like something like that you can see, or like for an object that size, how far, like how does that shrink that envelope?
Quite a bit. I would say probably half a kilometer might even be optimistic, but it's somewhere in that realm. And what makes this even more difficult is it depends on the temperature outside. It depends on the humidity, the cloud cover. All of these things impact
because the RF that impacts the RF. Is that what
Well,
is that
it
why?
could impact what the quality of the signal transmitted by the drone, but just in the optical, like optical infrared, you're dealing, the detection comes down to the contrast of whatever object you're interested on its backdrop. And so if you just think in extremes, like an extremely cold day with a hot object, that's going to be a lot easier to detect. Where you might have a really hot summer day with an object that's not very hot, um, won't contrast as much in your field of view. So then you throw in, okay, how does humidity affect that? How does the angle of the sun? That's another thing. Whereas if the sun is directly behind the camera in the direction you're looking, you'll have effects of how the infrared from the sun directly reflects off of that object. There's so many variables in this that will swing your detection volume one way or the other, and it changes daily. And that's what we have to account for when not going too extreme in what distances we set up.
Hmm. But I guess don't you kind of have to make some sort of call on the kinds of things you're looking for, and like to me, it just seems like if you're looking for like drone size objects versus 747 size objects, I mean, the system specs would be different. So, how did you guys decide, or like, is it right now? Is it pretty generic? You're trying to kind of get as much of this range as possible. Like you're like, is it kind of a middle of the road sort of system because you don't know what you're looking for? Like what? How'd you guys decide?
Yeah, I think probably erring on the side of caution in um, starting in nearby. Like right now, we have um, at our development site, we're testing triangulation with the second system only being 50 meters away, right? So that gives us birds and whatever targets are flying, every few minutes around our site. It lets us test out just the general functionality of, are we syncing the timing of the recordings and they're time stamped, and like kind of that basic, validation of functionality. We're checking that first, and then we'll probably move out to, we've done some testing at just several kilometers, 2, 3, 4 kilometers away. And that's probably like a good safe spot um, to target this year in the triangulation sites we set up.
What's the rough footprint of this? Like, how much space does all this equipment take up?
Yeah. So far, we've kind of floated around, I would say, about, let's say, like 60 or 75 feet by 75 feet. And that sometimes is oblong, or, depending on the obstructions around that site, we might kind of build it in an oblong shape. And we're working on bringing that closer and closer. I think each deployment we've done, we've brought the instruments a little closer, but the thing we have to look out for and that we don't fully understand yet is interference between our different instruments. They're not necessarily sending out these active signals that interfere, but one, you do have obstruction. Some of these are towers, and especially for the optical system, you don't want a bunch of towers in your field of view, so we'll space those out to at least 50 feet. But depending on how it's built, we're trying to bring that in tighter and tighter. And I know there are some sites I've looked at that are still in the works where we might try to bring it down to like 25 by 25 feet. So it really depends on what we're deploying and kind of our vantage point with it.
So I assume like if there's an academic or other private institution that says, hey, I want to be part of this. Like I have a rooftop with unobstructed view of the sky. I can write you a grant for the equipment. I'm assuming you're trying to get as many of those types of entities as possible. Like I'm assuming you're trying to build a lot of these, or are you kind of doing it very slowly? You're not at a point where you can really scale, or like, yeah. Tell me what's the vision of this? Like, are you at a point where like, hey, if a big check comes in, we're going to build 10 of these, or it's more like, oh no, this year we can just based on trialing the system, seeing what works, we can only build a maximum of 3 this year. Like, what? Tell me a little bit. What's the pace?
Yeah, that's an ongoing tug of war we need to figure out. Um, Obviously, if a donor were to approach us and they want a system set up on their property, and they'll pay for everything, and we've had that happen, of course. Um, it's great to get more instruments running, to get more data coming in, uh, but the size of our team is the size of our team, and it can take away some of that expertise and focus from our development system. It's sort of like quantity versus quality, right? Ideally, we would probably develop the functionality of the system, train the AI, fix some of the outages that we have.
It's more you're constrained more on the people resource end of things, or that's yeah, got it. One of the things that popped into my head while we were talking about the size of objects that you're trying to detect and what's the range, and when the subject comes of drones, so these are man-made objects, but like there could possibly be interesting anomalous objects of the same size. Uh, but there's a real commercial need right now to detect drones, even from a national defense perspective. And is there any sort of crossover in technology that you're aware of, or is what your application you're doing is very different? Because there's drone companies now that I think are working on drone detection technology. Is there any overlap, or is what you're doing pretty distinct?
We've run into overlapping sort of goals in technology where, one instance we've run into is there's a university project where the group is tracking birds. So they're using RF technology to see, what are these birds staying in the area? Are they migrating? And so then that kind of makes us wonder, like, okay, could that tech help us in some way? Is there something we could learn from that? And kind of more obvious would be, would some of our tech help their cause? Then you get into optics, infrared detection, some of those things. So, yeah, I think especially as AI is taking off, there are a lot of applications that come into play. The drones, as you mentioned, national, defense. There's probably areas where our tech will develop to a level that no one else has really put the time and energy into, and maybe in a combination way too, where we're not really aware of anyone else that's taking all these modalities kind of squished into one package.
So let's go into the AI machine learning aspect of this, which is like, is it kind of this, like having researched AI a bit, like, is it kind of this classification problem? Like first you're trying to figure out, I guess, natural, unnatural, and if it's not natural, man-made or not man-made? Is it kind of this 2-level binary classification? Or tell me what kind of AI problem is this, like at the highest level?
Well, I think the global approach that we're taking is to identify the known, and everything else we put to the side. And
identify the known. Okay.
Identify the known.
So it's binary classification, known or not known, kind of like that.
I would say that's like the top layer to it. We do have um, we do have our models trained for different categories. For instance, balloons, drones, planes, helicopters. There's quite a few categories the AI is being trained to, um, and it can effectively sort in that manner. As even with leaves, we probably have more leaves
Ah,
targeted
leaf
than anything
sightings
else. Exactly. Yeah, we have probably hundreds of thousands of those. But
of leaf sightings.
yep. So yeah, fall is a tough season for for detection.
Yeah.
So yeah, we do categorize in that manner, but it's easy to it can be too easy to get sidetracked or diverted from the goal if you're spending too many resources towards um, is this a helicopter or is this a drone? um, it's effective. We want that distinction. um, and I'm not the AI expert on the team, so I can
No,
kind of
oh,
give
I
the
see.
general, but
Mainly, as long basically you're just if it's known, you're not necessarily trying to get to another level of detail. Like basically, as long as it's a plane, I don't really care what kind of plane it is. As long as it's a bird, I don't really care what kind of bird it is, because what we're looking for is the unknown things.
yeah, everything that's known is just really a statistic in our data. At least from kind of my point of view, it's kind of clutter in a way we want to put to the side, and then what's left in our data set that the model just cannot figure out.
Okay. I have to imagine, since most of the things out there are known, uh, basically an ideal test run is everything is known, right? I mean, uh, so are you at that point now, or you're pretty far away where, this is still like, I guess, how far away are you at getting, kind of getting all the knowns identified?
Yeah, so I don't know exactly where we're at as of today, but I know kind of what will be seen in the paper that's out, um, on the scale of hundreds of thousands of objects have been detected and have been classified at least into some sort of kind of bucket of general identification. With those objects that are categorized, we also take those and train the AI. If those objects are established, if this is for sure an airplane, this is for sure a helicopter, since it's being seen through the modality that we're using, it's super valuable to train the AI algorithm on those known object cases. So we do use that as well. Um, we haven't gone completely through all of the data. Like I said, it's like tens and tens of terabytes. But there is a manual review element to it where we have to, if we run into something that isn't known or it just can't be identified, then that's where, we have to add a layer of analysis to it and step in and look at it.
So are you training it on like these broad categories? Like, so you're feeding it infrared data on birds, on planes, on helicopters, on leaves, and you're feeding it optical data on all these things too. Like, is that part of the training you're doing? Is just every known thing that's in the sky, you're trying to feed it data on this?
Yeah, I mean, if it's a good representation of that object type, then we feed it to the model for training. We obviously early on we didn't have that information, so we simulated what these objects might look like through that camera or through that modality by, kind of getting the right field of view. And that's a mix of, I mean, you might just take thousands of Google images of a helicopter and get a baseline training for that model by feeding it Google images. And then you also have a layer of synthesizing these objects in sort of a digital field of view layout and sort of training in that way. So we're training it in multiple ways.
So let me see if I got that. Like there's certain kinds of things you can, like Google Images and things where you can feed it data that actually, I guess, is already been labeled and you know what it is. Are you also training it based on the data you're collecting, where you collect the data and you label it and then you use that as training data as well?
Yeah, I believe if it's clear enough, if it's distinct enough, then it is data that we use to feedback through and train on.
Okay. It is. Do you know how intensive the training is at this point? Is it to a point where it's consuming a large part of the program budget? Like proportionally, is that a huge, is that a huge like expense or uh, at the moment?
I don't think expense wise it is. We usually have uh, a couple people on the project almost always, working on the training aspect of this, just ongoing. There have been instances where, and we've recently had a volunteer sit down and manually tag or label these objects. I think he went through, I can't remember if it was 14,000 or 40,000. Either way, it was a lot.
Of the data you've collected, he or she labeled the data that were collected through your instruments.
Exactly, yeah. Of the data we've collected to then, confirm this is an airplane, and then the model can be trained on that. So, early in the project, it was Google Images of, all these different representations of these categories we're interested in, people manually labeling these and ensuring they get in the right kind of bucket for the model to be trained on. So yeah, we're getting, as we run the instruments more, then we get the most realistic examples of what the camera can expect and what the AI can expect to see to run through the training.
Yeah. Do you know if anyone else do you know if there's any commercial interests that are gathering this kind of multimodal data about objects? Because it seems pretty unique. That's what I'm asking.
I think to the degree we're doing it, I haven't seen any commercial or any other examples of doing it to that scale. But I'm seeing more and more, especially the last couple of years of, even something like Zoom or these different applications that can detect, or like security cameras detecting a person walking by. They have something running to make that classification. But I haven't seen anything on this scale.
Because you're doing optical data, infrared data, radar data, and this ADS-B is not data you're collecting, but you're trying to, I guess, what do you call it? Correlate with that data.
Yeah, I would say where we're at right now, the brunt of the AI being used, and the machine learning activities are really going towards the visible cameras and the infrared. With, as we're kind of realizing success with that, and as we get some better baselines established with other instruments, then we can use that similar model and training method to apply it to, like with the passive radar. We also have what we call the Spectre, which, let's say a common commercial drone, someone's just flying their little drone around, and usually those are on like 2.4 gigahertz or something. This will basically plot all the radio frequencies it's detecting in the area passively, and sort of build up a data set of those detected frequencies over time. So that's a useful instrument that we're still kind of getting up and going reliably. But yeah, UV camera is one we're looking at in the future. There's so many acoustic system. So we're
acoustics.
measuring infrasound, the
Is that
sort of
a part of your current setup is acoustics as well?
it is. In fact, that was the first instrument to really reliably get up and running. Um, and like kind of like the sort of openness in the way we're approaching this, we don't know how interesting that's going to be. But if you have, if all the other modalities detect an object and establish that it's nearby, it's large, it's moving fast, and if the acoustic system has no detection of that, well, that's an interesting data point. Obviously, we're hearing aircraft all day. There's just constant aircraft noise, and um, that does have AI involved, and it's at a point where it can tell you this is some type of airliner, or this is a single prop airplane flying over, and we detect bats, we detect crickets, and it's training on all of that information.
Yeah, super interesting.
Yeah.
So it sounds like there's like a huge amount of work to kind of figure out the actual methodology that is rigorous scientifically on how to really research UAPs. So as that methodology gets refined, the chances that we'll find something increases. But also, if we do find something, there will be scientific rigor behind what we find versus some anecdotal thing, which is what we've been dealing with up until now. Many interesting anecdotes, but not a lot of scientific rigor. So I could see, having the rigor around this and the methodology itself would be a win.
Yeah. And even, in the years we've been operating, technology's noticeably changed. And so if there's something interesting that comes out this year, some type of sensor that's more sensitive in this area, or could be of interest in general to the public of, could this be used for detecting UAP? We're armed and ready to go in terms of, let's get it weatherized, let's get it implemented into the system, and let's see if it's something that could now, has reached a bar in sort of the tech tree where, okay, now this thing is sensitive enough, we're going to start seeing something.
Yeah, that's interesting. You can plug in possibly another modality. Once you have this overall methodology, you could plug in another modality, and now you've got like another set of eyes on this particular topic.
Exactly. Like even if infrared cameras, if they improve a lot, like I said, we're running a 640 by 512 resolution infrared camera, which, our webcams are double that at least. Who knows what more we could see with that if we had a 4K infrared camera. And that's the kind of stuff you get into, like the military can get their hands on a lot of stuff. Like if FLIR is making a lot of these cameras, they have a different catalog, a better catalog for the military than they do for folks like us. And so we're always anxiously watching for some of that tech to reach a point where, we can get our hands on it without, getting pulled into a classified setting.
Right. Or needing to spend, $1 million.
Yeah.
Right.
That's another huge part of one of our challenges. Yeah.
So I think it's very cool, and I wish you the best of luck. And I'm hoping for a big discovery in my lifetime. But even if it doesn't, I think it's a really noble endeavor. And there's a lot of amazing stuff out there, and I think it's a different sort of drive to want to do it scientifically, and really kind of discover, is this real in a very rigorous sort of way. I think that requires a particular kind of wiring, and I think it's cool that you've embarked on this journey.
Yeah, and going back to one of your earlier questions about like how do we set our milestones and metrics, or just knowing what we've done is successful. I think we've played a big part in terms of creating the conversation or creating just the awareness that, oh, okay, the stigma is going down a little bit, and somebody, just going into college or whatever can actually, if they have that thought of like, this subject interests me, where we're at now compared to 5 years ago. I mean, there are master's programs now where you can like study this topic. And so, if we achieve just one thing and it's opening up this topic for others to study it in a serious, technical, scientific manner, I feel like that's a huge success, because I think I can, confidently say there's something anomalous going on, and clearly no one in the public has figured it out. And it should be figured out, because it may affect how we understand reality, and it could open up areas of science and technology that could be used for the greater good.
Absolutely. I think that's a great place to end our conversation, at least this round of our conversation. Thank you so much, Ezra, for this conversation. I learned a lot, took a lot of notes, and yeah, best of luck. Of course, if there's anything I can do to help, let me know.
For sure. Thanks for having me, Tony.